Everyone's talking about the incredible power of AI chips from companies like NVIDIA, but there's this entire hidden world of physical infrastructure that makes it all possible. And that's what we're digging into today, the secret wires that are literally powering this whole AI revolution.
So let me just ask you this. As we're building these gigantic AI data centers, I'm talking tens of thousands of GPUs all trying to talk to each other. What do you think is the biggest traffic jam? The one thing that holds everything back?
You know, the answer might actually surprise you. It's not the brain power of the chips themselves, no. The real bottleneck, the thing that is actually slowing down this AI boom, it's the humble wire. It all comes down to connectivity.
To really get why, we've got to start with the tech we all know and love, copper. I mean, for decades, it's been the absolute workhorse for moving data around. But in the world of AI, copper is about to go right off a cliff.
Okay, so here's the fundamental problem. For AI to work its magic, you need data moving at just insane speeds, whether that's from one chip to another, from server to server in a rack, or all the way across a massive data center. But a standard, simple copper cable, it just gives up after about 1 meter. The signal basically turns into static. And in a huge AI facility, 1 meter gets you absolutely nowhere.
Now, engineers are obviously really clever, so they came up with a kind of workaround called active copper. What they do is embed these tiny little silicone chips, they're called retimers, right into the cable. You can think of them as little signal boosters that catch the data, clean it up, and send it on its way, letting it travel a bit farther. But really, it's just a temporary fix, a band-aid.
And this right here perfectly explains the real issue, which the industry has a great name for, the copper cliff. See, as we push to the next generation of speed, we're talking 800 gigabits, even 1.6 terabits per second, the signal just falls apart. It's not a gradual decline, it's an abrupt drop-off. The connection effectively dies. We've literally hit a physical wall with copper.
So if copper's hitting a cliff, what's the answer? Well, it's pretty elegant, and frankly, it's been right in front of us the whole time. We just stop sending electrons down a metal wire, and we start sending photons, particles of light, through glass. It's time for photonics.
So this is the world of optical interconnects, and the idea behind it is actually beautiful in its simplicity. You have a little device, an optical module, that takes the electrical bits coming off a chip, it converts them into photons, sends those little light particles zipping through a glass fiber, and then, at the other end, another device turns them right back into electrical bits. It's incredible. So how does this little piece of magic actually work? Well, inside this tiny module, you've got a few key parts, all working together. First is the DSP, or the digital signal processor. That's the brain. It's what prepares the electrical data so it can ride on a wave of light. Then you've got the laser, which is the heart. It does the actual conversion into photons. The fiber optic cable is like the superhighway. And then, finally, you have a receiver on the other side that catches the light and turns it all back into data the computer can understand.
Now that brain we just mentioned, the DSP chip, it is unbelievably important. This is a massively complex piece of silicon, and the market for it is pretty much a duopoly. MRVL technology is the giant here, with about 70% of the market, and Broadcom has most of the rest. This concentration of power makes the DSP one of the most critical choke points in this entire supply chain.
All right, so we get what these modules do, but how are they made? Because this is not like stamping out some simple plastic part. Forging a beam of light, it turns out, requires one of the most intricate and fascinating supply chains in all of modern technology. Looking at it from, say, 30,000 feet, it happens in 4 main stages. You start with sourcing these rare earth materials and growing perfect crystalline wafers. Then comes the really hard part, fabrication, where you grow these ultra-thin layers on the wafers to create the actual laser chips. After that is packaging, where everything gets aligned with microscopic precision. And finally, you integrate it all into the module and test it like crazy.
And here's the thing you have to understand. Each one of these stages has its own crazy bottlenecks. It creates this whole series of choke points. For the substrates, the very foundation of the lasers, there's a duopoly on a special material called indium phosphide. 2 companies, AXT and Sumitomo, control about 75% of the entire market. Then the next step, epitaxy, where you grow the active layers. The yields are just incredibly low. And the packaging, oh man, the packaging requires aligning things with sub-micron precision. It's so difficult, people in the industry literally call it a dark art, and only specialists like Fabrinet have truly mastered it.
But of course, the tech isn't just standing still. As AI keeps demanding more and more performance, the industry is facing this huge choice about how to actually use these optics. And it really comes down to 2 competing ideas: pluggables versus something called co-packaged optics.
Pluggable modules are what we mostly use today. They sit right on the edge of a circuit board, kind of like a USB stick for your computer. And they're awesome because if one of them fails, you just unplug it and pop in a new one. Easy. Co-packaged optics, or CPO, well, that's the future. In this setup, the optical engine is integrated right next to the main processor chip. This makes the electrical path super short, which dramatically cuts down on power use and latency. It's a game changer for performance. So you're probably thinking, why haven't we switched everything over to CPO already? Well, this chart tells the whole story. It's all about manufacturing yields. A mature pluggable module? You can make those with about a 95% success rate, but the first generation of CPO is getting closer to 60%. And here's the kicker. Because it's packaged right with that super expensive main chip, if the optics fail, you might have to throw out the entire thing. Ouch!
So the key takeaway here is pretty simple. Pluggables are going to be the workhorse for AI data centers for a good while. They're reliable, they're serviceable, but for that next leap in performance, for the next level of efficiency and scale, CPO is without a doubt where we're headed.
Okay, we've gone through the tech, we've gone through the supply chain. Now let's zoom out and actually map the ecosystem. Who are the real power players that control this critical emerging industry? First up, you have the foundational players. You've got AXT, making those critical indium phosphide substrates. There's MRVL, who we talked about absolutely dominating the brains of the operation, the DSP market. You have Lumentum, a leader in the high-performance lasers that actually create the light. And then there's Coherent, this vertically integrated giant that does pretty much everything from the raw materials all the way to the final modules.
Now you have the builders and the architects. Fabrinet is often called the TSMC of optics. They are the master builders who specialize in that high-precision assembly. Ciena is the long-haul architect. They dominate the market for connecting data centers to each other, which is a field called DCI. And then there's InnoLight, who right now is the #1 supplier of the final pluggable modules that go into all the servers.
So, why does all this matter so much? Why should you care? It comes down to this number. Analysts are projecting a 40 to 60% shortfall in the supply of these high-speed optical transceivers all the way through 2027. Demand is just going through the roof, and the entire industry is in a mad dash to try and keep up.
All right, so let's just quickly recap the big points. The copper cliff is forcing a massive industry-wide shift from electricity to light for moving data. The supply chain for photonics is wildly complex, with key bottlenecks controlled by just a handful of specialized companies. And while pluggable modules are running the show today, the future of high performance and efficiency is definitely co-packaged optics. And that kind of leaves us with one last big thought. Photonics today really is a foundational technology. It's quietly powering everything, a lot like semiconductors were decades ago. So the big question for the future is, as this new era of light-based computing really takes off, who is going to be the next Intel?